Howdy, and welcome to our first full look at hypothesis testing. This is where we're finally going to put everything that we've studied so far to use and actually complete a hypothesis test in full. In this particular case, we're going to be looking at a test for a mean that's going to use a z-score. So something where our sample size is big enough or we know enough to be able to just use the normal distribution. In this case, we're going to be looking not at p-value testing just yet. That will come very, very soon. But in this case, we're only looking at using critical values, at just understanding where a cutoff for what we would consider a significant change would be, and how to analyze, how to draw conclusions from either having or not having that significant difference. So let's first look at exactly kind of the process that we're going to be using. You've done some of these already. So namely we've talked about steps 1 and 4 in particular already. The part where we design a study, we're going to talk about how you would set things up, what you need to think about. That's a discussion for another time. And in conducting a study and collecting data, we've talked about much earlier in the course. So we've recently discussed steps 1 and 4 here, and we're going to put these into context now and talk about what we mean by step 5, to what we mean by summarizing results or drawing conclusions. So what we need to be working with is our first approach here is going to just be to find a z-score for a critical value and then compare this to a z-score for our observed data, with the idea that we're going to reject our null hypothesis if and only if the test value is more extreme than the critical value. So further from our presumed mean, further from our hypothesized, our null hypothesized mean of whatever our baseline is, than the critical value is. So if our test value is further from that hypothesized mean than our critical value, then we know that that's evidence against the null hypothesis. And this is the idea. A critical value just gives us a certain kind of breakpoint, essentially, where we say, like, okay, this is far enough away that it's evidence against it's evidence against the null hypothesis, enough so that we choose to reject it. Reject the null, I mean, not reject the evidence. So the idea here is that what we're going to be doing in this method is comparing z-scores. And this is a reminder that the z-score for actually, a computed value for like a sample mean is going to be the sample mean minus the whatever our presumed population mean is, whatever our baseline is, over the standard deviation divided by root n. And this standard deviation might take the form of a sample standard deviation instead of the population standard deviation. And then that's fine, because when we collect our sample, we're collecting the sample under the assumption, or under the presumption rather, that the null hypothesis is true. So the sample standard deviation should, if things were unchanged, or if things were as the null hypothesis would suggest, it should match our presumed population anyway. So it's fine to be using the standard deviation from your sample in this calculation. So when we talk about computing a test value, we're really just finding that the test value should be whatever we're observing minus whatever we were expecting, quote unquote expecting, over the standard error. And this is just this is just kind of putting this particular equation into context. And we've certainly seen this before. I mean, we talked a lot about finding z-scores using this equation when we began discussing the central limit theorem, and I kind of said that this standard deviation over root n as the standard error was going to be our new standard, that that there were only going to be very rare occasions where we weren't dealing with this definition of standard error anymore. And once again, our rule of thumb is if your sample size is greater than or equal to 30, you get to use you can treat your distribution like it's normal. You get to use the z-table. Again, that's a sort of arbitrary rule of thumb, but it's one that we'll follow. So, the thing that we've done here is we're just going to compute z-scores in the normal way. So we have this example of we're testing, we have this just, obviously theoretic example of saying, all right, we want to test if there's been an increase in the number of honey badger attacks. So maybe, before 1940, there was a mean, of 3 attacks per month with a standard deviation of 1.6. We sample 100 month since and find a sample mean of 3.5. Let's say it's got the same standard deviation roughly. So we want to know, what's the z-score for this test value where we have, a sample of 100, a standard deviation of 1.6, a sample mean of 3.5. What happens here is we say, okay, well, we're testing this against 3. We're testing this under the assumption that the mean should be 3. And so, well, the null hypothesis is saying the mean is 3 anyway. So we get a z-score of 3.5 minus 3 over 1.6 divided by root 100, which gives us 3.125 as a z-score. And while we're here, we'll note that the null hypothesis would be that, the mean is less than or equal to 3. The alternative hypothesis, the mean is greater than 3. This is a right-tailed test because we're testing for an increase. And so what would happen here is what we're missing is picking a level of significance, picking an alpha. And in any real test, we'd have done that ahead of time. We would not be computing anything before finding an alpha. If we were going to try and be, absolutely rigorous in our work. Or we'd have, we would have an established idea of what a useful alpha would be before we even began. Or a reason to pick one at least. So what we're going to do here is is in the next slide, we'll compute a critical value for, and we'll choose alpha equals 0.05. This is a right-tailed test, so the critical value is 1.645. We've discussed in the past how to find that. I'm going to point out another nice way to do that in the future. This was your last assignment. This was the last discussion I had. The last slideshow we went through talked about exactly how to find a critical value for given alphas. And so the test value was 3.125. 3.125 is certainly more extreme than 1.645. Further from 0. That's really all more extreme means, is further from 0 in the same direction. So it's certainly more extreme than our critical value of 1.645 and means that this z-score is in the critical region. So we conclude that we should reject the null hypothesis. And this would be, in terms of, from a procedural standpoint, this is the end of our hypothesis test. We've laid out our hypotheses. We've laid out what our benchmark for rejection would be. We've tested. We've used our sample values. We've come up with a test value. It went past the benchmark, so we reject the null hypothesis. This is the full procedure of a test. So the big thing here is that this is essentially getting a z-score from our test value that's this extreme is evidence that's just suggesting that the assumption the null hypothesis makes is not a good one based on the data we collect. So that's why we reject the null hypothesis. So this conclusion is always just reject null hypothesis or do not reject null hypothesis. It's never accept the null hypothesis. And the reason for that is really just because the evidence we're collecting is always evidence that is um, placed on a normal curve or placed on a curve where the assumption is that the mean is the is the hypothesized mean, is the base, is whatever baseline we're basing our hypotheses around. And so um, so the idea here is if our data points are relatively central, then it's just not evidence that particular distribution shape was a problem. It's just a lack of evidence against the null hypothesis. It's not that we're arguing like, oh, yep, no, we accept it now. Just no, we didn't find evidence against it. That's not quite the same thing. So yeah, I will be militant about this. I want none of you to ever tell me that you're accepting the null hypothesis, because you're not. I will be militant about that. So ultimately, though, our real conclusion is to interpret this statement in context. So what is, rejection or non-rejection actually saying? So here, our rejection of the null hypothesis is really saying that evidence suggests, if you go back to this previous slide of what we were starting with, evidence suggests that we reject the null hypothesis, and that evidence suggests that we should reject this. And what that means is evidence is suggesting that the number of honey badger attacks is indeed above 3, because we're rejecting that it's equal to or below 3. So that's the kind of conclusion that we're going to draw. And you really don't want to say things, again, I'm going to be militant about this. You don't want to say things like the number of honey badgers attacks is above 3. No, you don't know that. Evidence suggests it is, but you don't know that. You don't know it for sure. The best you can do is say, yeah, we're essentially making, for all intents and purposes, an educated statement about our assumptions, or an educated guess, if you want to kind of shorthand it, though that's really not precisely accurate. But we're really just kind of making a statement based on evidence, not an absolute conclusion. Again, I'm going to be militant about that. In terms of alternative ways to find a given alpha, the t-table, once again, is actually a nice shortcut here. We've already talked about finding critical values in the normal way, just using a z-table. But if we go to the t-table, it's actually going to help us out. So we wanted a one-tailed test for alpha equals 0.05. What we can do is, at the top of this table, you see something that says one tail, two tails. If I just go across to one tail, 0.05, and then go down until I get to the bottom of the table where there's this z, this tells me the z-score for that level of significance in a one-tailed test, 1.645, as claimed. If instead I had wanted an alpha of 0.1 in a one-tailed test for some reason, that's insane, but hey, whatever, just an example. If I wanted an alpha of 0.1, I would just go down here and it's okay, it's great, it's 1.282. If I wanted, an alpha of 0.01, it would be 2.326. If I wanted a two-tailed test with an alpha of 0.05, that would be 1.96. I would, go across two tails to 0.05 and down to 1.96. You might notice, by the way, and this is, for obvious reasons, I hope at least, not accidental, all one-tailed tests in the same column are half the alpha of all two-tailed tests. And that's because the two-tailed tests are occurring on both sides of the distribution. The one-tailed test is only on one side. So if you're going to have the same cutoffs, then the two-tailed test had better be twice the size of the one-tailed test, because it's got twice the region. So yeah. Let's go back to the slideshow and we'll go through some examples. Once again, by the way, remember, if you're using the t-table, that's only giving you positive z-scores. that doesn't mean that all your critical values are positive. If you're doing a right-tailed test, it's got one positive critical value. If you're doing a left-tailed test, it's got one negative critical value. So you need to pretend that the z-score, you need to just, not pretend, but you need to take the z-score you get from that table and stick a negative sign in front of it. If you're doing a two-tailed test, there's two symmetric scores. One's positive, one's negative. So you'd say, like, you know, the critical values we have are plus or minus 1.96. So let's take a look at an example. So an experimenter wants to know if assistant professors make, you know, greater than $42,000. A study of 36 such employees gives a mean of 43,260, standard deviation of 6,000. So let's test if this is a true statement using, or not true, if this is a true statement, but let's test if this is a reasonable conclusion to draw, that assistant professors make greater than 42,000. Based on alpha, or using alpha equals 0.05. So we get that the null hypothesis is, because this is a right-tailed test, we're looking for an increase. We're looking to be above 42,000. A right-tailed test, so mu is less than or equal to 42,000 is the null. The alternative is mu is greater than 42,000. Our critical value here, just as we just, you know, did something that had an alpha of 0.05 in a right-tailed test, so the critical value is the same, 1.645. Our test value, sample mean minus our baseline, minus whatever we're comparing to, minus whatever we've, you know, assumed for the null, over the standard deviation divided by root n. So we get 1260 over 1,000 is 1.26. 1.26 is not more extreme than 1.645. So this means this is not in the critical region. If we want to see kind of what that would look like, it's essentially saying something like this. If we have kind of our normal curve, yeah, that's terrible. Let's try that again, this time with a nicer curve. If we have our normal curve and our critical region is, you know, right here, this is our 1.645. There's a shaded area of 0.05 here. Did not take kindly to that. Our actual found value of, I believe it was 1.26, would be, you know, somewhere like right here. Which, you know, this is not in the critical region. So this is not a place where we reject the null hypothesis. It's not extreme enough. So this is, you know, this is what we do. This is what we're looking at. So we do not reject the null hypothesis here. And what that means, non-rejection of a null hypothesis, all this is saying is we have not found the necessary evidence or significant evidence, or we have not found any notable evidence suggesting that the null is incorrect. So we haven't found significant evidence that assistant professors make over 42,000. And that's our conclusion. This is a full hypothesis test, at least a full bare bones hypothesis test. Usually you'd be a little more, you know, you'd be a little more detailed in this and what in performing these tests than this describes. But this is a full, like, this is the full, at least general procedure that you would go through. So let's try another example. Again, an experimenter wants to test if sleep habits have changed since the advent of the digital age. And he wants to test this with a significance level of alpha equals 0.01. So let's say in the past, let's say sleep in hours per night had a distribution of a mean of 8 with a standard deviation of 1. And a recent study of 64 subjects found a sample mean of 7.5 hours. We're going to assume with the same standard deviation. Our null hypothesis is that the mean the mean that we're testing should be 8. The alternative is that the mean that we're testing is not 8, because again, we're just looking to see if there's a change, a difference, right? So it's a two-tailed test. So here, two-tailed test, alpha of 0.01. I'm gonna, we've talked plenty about using a z-table for doing this, so I'm gonna point out the t-table here. We would just go two tails, alpha of 0.01, 2.576. And since it's two tails, it's plus or minus 2.576. So those are our critical values. That's all you have to do to find those. Our test value is 7.5 minus 8, right? Sample mean minus population mean, if you want to, if you want to set it up that, if you want to call it that. But yeah, sample mean minus our assumed mean over the standard deviation, 1, divided by root 64. So here we get negative 0.5 over 0.125, which gives us negative 4. And this might happen sometimes. If there's a pretty definitive answer, you might end up with a test value which is incredibly extreme. And I mean, negative 4 is not incredibly extreme, but it's pretty freaking noticeable. Yeah, that actually is pretty extreme. Kind of, if you think about where this is on the z-table, it's off the end of the table. But you might get z-scores that are insane, and if so, that means yeah, there's a pretty noticeable difference. That can happen. Oftentimes when something's that extreme, what's happening there is either whatever difference you were looking for is pretty definitively there in your data, or it can mean that maybe sometimes we get these because sometimes we end up with these things because someone's designing an experiment that was kind of a waste of time. So this happens a lot in I would say studies that don't really get published, or in my experience at least, many undergrad psych projects that are just looking to conclude something for the sake of concluding something. I have seen a lot of these where they end up not necessarily using a critical value, but p-value testing, because that's a more acceptable thing. But they end up in their process coming across what amounts to a z-score that's absolutely insane. That's very, very, very extreme, and that's because maybe the premise of the experiment wasn't particularly interesting in the first place, or was pretty obvious in the first place even. But yeah. So anyway, back to this. What we have here is we have a z of negative 4, and this is extreme, but not as extreme as you'll see, I would suspect. But anyway, this negative 4 is definitely in the critical region, or the negative side of the critical regions for our two-tailed test in particular, because this negative 4 is certainly more extreme than negative 2.576. Again, we compare it to the direction that we compare it to a critical value in the direction that we're looking. And if it were a one-tailed test and on the wrong side, well, there is no critical value on that side, so we definitely can't reject. And that's one of the issues with one-tailed testing. Anyway, since this test value is in the critical region, we reject the null hypothesis. So in this case, evidence suggests that sleep habits have changed in the digital age. And we can even append to this with our particular sample finding lower values. It's fine to append that. There's nothing wrong. There's nothing wrong with saying yep, and in particular, our values were lower. The main conclusion is what's not in parentheses. The main conclusion here is that the evidence suggests sleep habits have changed. And this is the full of what I want to talk about in terms of introducing at least this critical value method of hypothesis testing. You can see that there are a few more slides in the show. The remaining slides in the show talk about, instead of using z-scores, making your cutoff of critical values using data values themselves. So instead, you would, turn your critical value into an X value, into an actual cutoff in terms of the data you collected, or in terms of what the mean would actually be, as a applied number. Sample mean, I mean. And this is just another way to do the exact same test. I don't know if I've ever seen this used, but it is logically equivalent. So I included it in the slideshow just as, something that you might be interested in doing, but I'm not going to discuss it here. Instead, what I'm going to do with the last few minutes of this lecture are, I'm just going to set a problem fresh here. So let's assume that God forbid, our reason for being at home right now continues for quite some time. Hopefully not, for obvious reasons. Hopefully not, but let's say that this happens, and eventually I want to test if the amount of exercise I'm getting, or someone wants, Billy Joe Jim Bob wants to test if the amount of exercise he's getting has decreased, because he feels that he's maybe leading a more sedentary lifestyle now. So what he does is he says, well, I used to get, before everything, before everyone kind of was on stay-at-home orders, I used to get 30 minutes of exercise a day, and now I'm not sure if I'm, and now I'd like to know if I'm, if I'm kind of under that. This might be a rare example where I would say a one-tailed test is actually proper. Because it's, the increased testing power might cause him to recognize something he would have otherwise missed. Might cause him to find significance in something that a two-tailed test would have missed for a similar alpha. It's not life or death into whether or not he makes a type 1 error. Whether or not he concludes that he should reject the null hypothesis when he actually shouldn't have. It's not life or death if that happens. Or it's not even a big deal if that happens. A value that's actually in the wrong direction of what he's testing probably would mean he would make no change, probably would mean that would affect him in no way. So this might be a rare circumstance where I would say a one-tailed test is reasonable. This is I reasonable. I still wouldn't do it personally because I hate them, but reasonable. So let's go ahead and discuss like things that we're looking at here. So first things first, he's wanting to test if his mean time spent exercising has dropped below, has gone below 30 minutes per day. So his hypotheses, let's kind of set those, his null and alternative hypotheses. His null would be that's definitely supposed to be a mu. Shut up, it is. His null is definitely that the mean is greater than or equal to 30 minutes per day. His alternative is that the mean is fewer than 30 minutes per day. So let's say that he goes ahead and let's say that he wants to test this with, that is an awful alpha. Let me try that again. Let's say he wants to test this with alpha of 0.5 or 0.05, sorry. And let's say that he samples, he collects a sample and he finds that he's got a sample mean of, let's say, 25 minutes. So, maybe this is less, maybe this is significantly less, maybe it's not. We'll find out based on the rest of the information we have. He finds that there's a standard deviation, his sample standard deviation, which again, for all intents and purposes, we can treat this as a population standard deviation of, let's say he has one of 16 minutes. And let's say that he sampled a total of 40 days. So as I said, God forbid it goes this long, but that's the assumption we're making. All right, so first off, we have a left-tailed test. We have alpha of 0.05. This is, I'm actually going to switch type here. This is going to imply a critical value of z is equal to negative 1.645. And how did I find that? Well, I went to my z table, or my t table in this case, and I just say, well, one-tailed test, 0.05, 1.645, but it's left tail, so it's negative. And that's my critical value. And now I want to compute my test value. I want to compute what I'm going to compare to that critical value. So, my test value, my sample value, or my value coming from the sample anyway, is going to be the sample mean minus my baseline minus my source of comparison over the standard deviation divided by the square root of my sample size. And this is going to be approximately equal to -5. Obviously, that is equal in the numerator. The denominator is approximately 2.53. And that's going to be negative 1.98. Now, what happens here is if I take a look at my normal curve, this is where, this is where my negative 1.645 is. This is where my critical value is. The blue shade is my critical region. And what I have here is negative 1.98 is going to be right there ish. Obviously just sketching that, but it's going to be right there, which is firmly in the critical region. Not extremely so, but it is. So in this case, our conclusion is that since our test value is more extreme than our critical value, our conclusion is to reject the null hypothesis. And once again, you're not really done with an experiment until you're not really done talking about this until you've actually put it into context. So Billy Joe Jim Bob here concludes at least that his evidence suggests that his amount of time spent working out per day has gotten lower. That's what the evidence suggests. That's what the evidence here is suggesting. So yeah, that's really it for kind of what I want you to be doing kind of at this early stage of understanding hypothesis testing. So an important note to make, and this is the last thing I'm going to say before kind of closing this video, is that our alpha, is a very important piece of our experimental process. And what our alpha represents is the maximum probability that we are willing to have that we made a type 1 error. The maximum chance we want to have that we've made the mistake of rejecting the null hypothesis when maybe it was actually true. So I in this case, setting an alpha of 0.05 says I wanted no more than a 5% chance of being wrong in rejecting the null hypothesis. We'll refine that we'll refine that line of thought when we discuss p-values, because one of the strength of p-values is it's a direct assessment of probability. It's a direct assessment of how likely we are to make a type 1 error. Um, so we'll refine this statement as we get toward p-value testing, which is the preferred method. But for the time being, you can think of alpha as the maximum level of the maximum probability where you're willing to, of making a type 1 error. The maximum probability you're willing to accept. So yeah, until next time.